Guys, hello.
Yes, sir.
Yes, sir.
Visible.
So one of the most important feature of operational amplifier is it exhibits what is called as a virtual short circuit. Now let us see what that exactly means. So if you have your operational amplifier, we have already seen the symbol yesterday. You all know what are the various pins now. Okay, so this is, let us say, V1, this is V2, this we know is inverting, this is non-inverting, and whatever here we have is the differential input voltage. Let us say the current flowing here is I. Okay. We already know that VO is A into VID. So point number one, A, or point number A. What is the input impedance? What is the input impedance of an ideal operational amplifier? Yesterday we have seen the characteristics of ideal operational amplifier.
So infinity. Infinity.
Ri, yes, Ri is infinity. Okay. Now, if Ri is infinity, and if you look at the internal, let us say, the model of operational amplifier, this is what is Ri. I'm just partially drawing it. This is VID. So if Ri is infinity, what will be the value of this current I? Since Ri is infinity, I is equal to what? Ohm's law? Guys? Guys, tell me the answer.
So zero.
Absolutely
Zero,
correct.
sir.
So what do you mean by this? It simply means that no current flows into the op-amp terminals. This is a very, very important thing. Okay? Is this fine up to this point? Because you
Yes,
see
sir.
that Ri, this is I, which is the current flowing into the op-amp, which is given as this, which is nothing but VID by infinity, which is equal to 0.
0.
Okay. Now concentrate on the output side. We have VO, that is the output voltage given as A into VID. Okay. Now what is this A, or large signal voltage gain of an ideal voltage amplifier, ideal op-amp? What is the value of A for ideal op-amp? Yesterday we have seen that.
Sir, infinity.
It is infinity, right? So since A is equal to infinity for ideal op-amp, can I write it like this? VID is equal to VO by A. So it is equal to VO by infinity. So what is the value of VID?
Sir, 0.
0.
0.
Look at these two things. I is equal to 0 here. VID equal to 0. When do we have zero voltage difference between 2 points?
So when resistance is 0.
Resistance 0 नहीं बोलते हैं उसको. When both the
Short
potential difference are both the voltages are same.
Yes, sir.
Or you have, yes, some other way around. Let us say that if the resistance between the 2 points is 0, as somebody said correctly, then the potential difference between those points is 0, right?
Yes, sir.
Such a situation, what do we say? If this point is directly connected to this point, what do we say? We call this as short circuit, isn't it? We say that point
Yes,
A
sir.
and B are short circuited.
Short circuit.
Okay.
Yes, sir.
Yes.
Now look at the most interesting thing here. It is not as per whatever we have seen or experienced till now. What does it say? It says that there is a virtual short circuit between this terminal and this terminal. There is a short circuit, as if there is a short circuit because VID happens to be 0, right? Is that okay?
Yes, sir.
Guys? That is fine, no?
Yes, sir.
Okay. But when we have a short circuit, what is the current that flows into a short circuit?
So infinite current.
Infinite current, isn't it? So if this is, let us say, 10 volts, and if you directly short it to ground, the resistance being 0, the current I will be infinite. So even though there is a short circuit across the operational amplifier, that is, even though both these terminals V1 inverting and the non-inverting are at the same potential, that is, they are short circuited. In spite of that, mark my words, in spite of that, what is the current flowing between them? It is
0.
0. Isn't it interesting?
Yes, sir.
We have a situation here where both the points A and B are short circuited, but still there is no current flowing between these 2 points. This is marvelous. This is interesting. And this is very, very important. And you are going to see there are so many advantages associated with this virtual short circuit. Basically, the working of operational amplifier is so because of this virtual short circuit. Why do we use this word virtual? Because even though there exists a short circuit between inverting and non-inverting terminals, no current flows through this short circuit. There is one more, let us say, effect to that. And what is that? So whenever I supply voltage to one particular terminal, let us say negative or positive, doesn't really matter at this point, inverting or non-inverting. So if I raise this voltage to 1 volt, what will be the voltage over here? Guys, because of the virtual short circuit, this also will be
1 volt.
volt. But it is not going to happen directly like that. We are going to see how it happens actually. Okay. It also means that one important observation is that since A is, that is the open loop gain is infinity, ideally a very small value of VID will produce a large output. This is nothing great, but the output is limited by the power supply voltages as we have seen yesterday, and so therefore, but due to supply voltages being limited, output VO will go, let us say, will be saturated, or I can say the output, the operational amplifier gets saturated. In fact, this is also what we saw yesterday when we talked about the transfer function of the operational amplifier, if you remember that. Transfer function was something like this. So this transfer function, this is your VID, this is VO, okay, and this is a very limited, this is your VID where the output remains, I mean, the operational amplifier really behaves as an amplifier. After that, you can see that it goes into either positive saturation or negative saturation. Okay. Is this concept clear to all of you? Three important things. One, the concept of virtual short, how it happens, because we have said that Ri, input impedance, input resistance between the two terminals, inverting and the non-inverting, is infinite for ideal operational amplifier. So there is no current flow. It is as good as open. But at the same time, since A is infinite, there exists a virtual short circuit between point A, that is inverting input, and the non-inverting input. So this is a strange thing where you actually have a short circuit, but there is no current flowing between this short-circuited points. Clear? Guys?
Yes, sir.
Are you absolutely sure? Because this is the most fundamental thing. If you understand this, everything will be easy for you as far as the applications of the operational amplifiers are concerned. So I hope this is absolutely clear, crystal clear. Yes? Are there any doubts, any questions up to this point? Hello? Guys?
No,
Please respond. Please respond.
no, sir.
No, sir.
Everyone, is it clear?
Yes, sir.
Yes, sir.
Okay. So now let us go to a slightly different part. Once we are finished with the concept, let us now see the practical op-amp. Now we have seen ideal. Let us see the practical op-amp and its various parameters. Okay, now let us come to the reality. Till now it was easy for us because we were assuming the operational amplifier to be ideal. So an ideal op amp, we already said that it is perfectly balanced. So if V1 equal to V2, then Vout equal to 0. That is for ideal op amp. But the real op amp, so this was the perfect balance. For a real op amp, an imbalance will be there because of transistor mismatch. Whatever we do, you cannot have 100% identical transistors. Okay, that is in your differential amplifier. And so because of this transistor mismatch, there will be an imbalance. This mismatch will result in what is called as unequal bias currents. If you remember this differential amplifier, so because these transistors are really not 100% matching or identical, there will be some imbalance, and because of that imbalance there will be some unequal bias currents. These are the biasing currents, or maybe even these are also the biasing currents. So IC1 and IC2 may not be exactly equal, and since they are not exactly equal, IB1 and IB2, which we were assuming to be equal, are also bias current. So this input bias current IB is defined as the average of IB1 and IB2. Okay, so if I am having an operational amplifier, so in that case IB is defined as IB1 plus IB2 divided by 2. So it is an average value of, this is called as the input bias current. Okay, most of the time this is going to be a very small value, mostly in nanoamperes. Okay, so please remember that. Ideally we were expecting it to be 0, but now we are talking about a practical operational amplifier, and so this IB1 and IB2 being non-zero, IB also is non-zero, and so we have some very small value, but it will be in nanoamperes. Okay, but remember these are the biasing currents. Okay, are you able to understand this? For a typical IC called as LM741, which is a general purpose operational amplifier, which is very famous. Variant of that is LM741C. this IB happens to be 500 nanoampere maximum. This is what is given in the data sheet. Okay, guys,
Yes, sir.
did you understand the input bias current first of all? Why was
Yes,
there
sir.
an imbalance? Because we said that these two transistors Q1 and Q2, they are not really perfect, 100% perfect. So their collector currents IC1 and IC2 may not be exactly equal. And since IC1 and IC2, of course, this is ICQ, the quiescent current. Since IC1 and IC2 are not equal, we also said that IB1 and IB2 will also not be equal, number one. And number two, input bias current is then defined as the average of these two currents. Remember that. And for typical operational amplifier called as LM741C, IB happens to be 500 nanoamperes. It is the maximum value given by the data sheet. All right. This is one parameter. Another parameter is called as the
Yes.
input offset voltage. A very important thing. Okay. So this is actually defined as the voltage that must be applied between the two input terminals of op amp so that VO becomes exactly equal to 0. Now this is interesting and this requires some explanation. As I said, we were expecting that V1 equal to V2. In that situation, VO should be 0. Okay, that is in perfect balance. But because of the imbalance, it so happens that basically the input bias currents of themselves are not equal. And if they are not equal, there will be some output voltage corresponding to that. Simply means that even if I don't apply any voltage, or even if I do something like this, remember there will be some IB1 here, there will be some IB2 here, and we were expecting that in both the situations, I mean, when both the inputs are 0, that is V1 equal to V2 equal to 0, we were expecting V out to be equal to 0. But because of this imbalance, you will be having a non-zero output voltage. This is called as the output offset voltage. It is an offset. Remember, I am not applying any input. And no matter what you do, you cannot have 100% matching of the transistors. That is the reason why there is an imbalance. And because of that, you get the output offset voltage, which is a non-zero value. Now it says that Guys,
Yes, sir.
there was a call drop because of the internet problem. I've restarted. So I think it is it visible now?
Yes, sir.
Right? Are we
Yes,
back
sir.
online? All of you?
Yes, sir.
Okay. So I was talking about the input offset voltage, right? So now if I apply something over here, so I'll call this as VO. VIO 1, this voltage, and this voltage I'm going to call as VIO 2, and the net voltage VIO is VIO 1 minus VIO 2. This VIO is nothing but the input offset voltage. It simply means that I have to apply some voltage difference between the input so that I can have V out to be exactly equal to 0. That is, I'm actually trying to compensate for the output offset voltage. Are you able to understand this, guys?
Yes, sir.
Hello? So what is
Yes,
input
sir.
offset voltage? It is the offset voltage which I have to provide so that the output voltage becomes 0. This should be your starting point. Okay. Now this VIO can be positive or it can be negative. So normally the data sheets will tell you the absolute value. Okay. Now for our example device 741C, LM741C, which is a typical and popular operational amplifier. This VIO happens to be 6 millivolts max. So what do you mean by that? The manufacturer says that in order to have or compensate for the imbalance or the output offset voltage, you have to first of all apply 6 millivolts at the input, of course DC, so that output voltage will be equal to exactly 0, and then you can start working with it. It is like, guys, it is like your weighing scale. It is like your weighing scale. Many of you have used this mechanical weighing scale, yes, for measuring your weight, guys.
Yes, sir.
Okay, so what is the very first thing that you do? You don't simply jump on the top of it and start looking at the scale, you know. First of all, what you see is what is the current when there is no weight on the scale. What is it pointing to? I mean, what does the output say? If there is some error, what do? You adjust it to 0 first. Isn't
Yes, sir.
it? That
Yes, sir.
offset you remove, and then you start measuring your weight. It is very, very similar to that. Okay? Now, smaller the value of VIO indicates better is the op amp. So this is again one of the figures of merit. Okay. So we have seen the input offset voltage. Next is the input offset current. Now guys, this is actually a very dangerous thing. Offset voltage in operational amplifier is a very dangerous thing. I think I'll talk about it in more details when we actually see why it is so dreadful. Okay, let us concentrate on this input offset current. It is nothing but the algebraic difference between the currents flowing into the input terminals. Okay, so I can call this as IIO, which is nothing but IB1 modulus of IB1 minus IB2. Simple. Don't get confused between the input bias current and the input offset current. For LM741C, this value of IIO is given by the manufacturer to be 200 nanoamperes max. Again, lower the value of IIO, better is the operational amplifier. Okay? Next, the differential input resistance. It is the equivalent resistance that can be measured at either the inverting or the non-inverting terminal, while the other terminal is connected to ground. In simple plain words, if I have an operational amplifier like this, so if this is connected to ground, what is the resistance measured over here? Is nothing but the differential input resistance. That's all. Okay. For 741C, this differential resistance happens to be about 2 mega ohms. Please understand this carefully. Okay. Now there are special purpose operational amplifiers where we require the input resistance to be as high as possible, even higher than this. Okay. And those normally make use of feed effect transistors at the input. So your differential amplifier is composed of FETs. And all of you know that FETs, the input resistance for FET is tremendously high. So with such inputs, they are called as a FET input or JFET input op amps. And their differential input resistance is in thousands of mega ohms or even more than that. Okay? Another important factor is the input capacitance. Okay, this input capacitance Ci is the equivalent capacitance that can be measured at either the inverting or the non-inverting terminal with the other terminal connected to ground. So in a similar way, one of the terminals is connected to ground. So whatever is the capacitance between this terminal and this terminal is called as the input capacitance. Typical value of Ci for 741 is 1.4 picofarad. All right. Clear up to this point, guys?
Yes, sir.
Yes, sir.
Okay. Now there are other things which we'll see first, and then okay. Another important parameter is the input voltage range. What is this input voltage range? For 741, see the range of input common mode voltage is plus minus 13 volts max. What do you mean by this? It simply means that the common mode voltage applied to both the input terminals can be as high as plus or minus 13 volts. That is as high as plus 13 volts, the negative side as low as minus 30 volts, without disturbing the proper functioning of the operational amplifier. Okay, this is what I mean by input voltage range. And the next important parameter is the CMRR. We already have seen what is the CMRR, and this actually is equal to the differential mode gain by the common mode gain. So where AD is the differential voltage gain, which is the same as the large signal voltage gain, which is specified in the data sheet. Okay. CMRR we have already seen is most of the times expressed in decibels. Okay, for LM741C, the CMRR is 90 dB typically. Okay. One more important point or parameter is the supply voltage rejection ratio. Okay, also called as a supply. It is having an acronym of abbreviation of SVRR. So supply voltage rejection ratio. It is also called as power supply rejection ratio, PSRR. All these are synonyms. Also, power supply sensitivity, PSS. Okay. What does this mean? What does this parameter mean? Now, the change in an operational amplifier's input offset voltage VIO is caused by, many times caused by variations in the supply voltages. Okay. Now, this is actually very dangerous thing, because if your input offset voltage itself is changing, the output will change by A times. You know that A is very large, so this is a very dangerous thing. And this change is expressed in terms of what is called as a SVRR or PSRR or PSS, and is in microvolts. So what are the units? Microvolts per volt, or also expressed in dBs. Okay. So remember that power supply also plays a role in changing this, and so how strong the operational amplifier design, internal design is, so that it will reject the changes in the power supply is shown by this factor. So SVRR is delta VIO by delta V. What is this delta V? This is change in the power supply voltage. For LM741C, SVRR happens to be 150 microvolts per volt. Guys, are you able to understand this? Hello?
Yes, sir.
Are you all
Yes,
with
sir.
me?
Yes,
Yes,
sir.
sir.
Yes.
Okay. So these are very, very important parameters, and that is the reason why I'm concentrating more here. The next parameter is the large signal voltage gain. The thing that which we had denoted as A. But how is it specified? Since your operational amplifier will amplify difference between the two input terminals, the voltage gain of amplifier will be defined simply as voltage gain is equal to output voltage divided by the differential input voltage. So we have A, which is equal to VO by VID. We already have seen this. No issue with that. Now, again, I've already said that whenever we talk about voltages in 10 volts or tens of volts, we call it as a large signal. Okay, whereas if the signal is in microvolts or millivolts, you call it as a small signal. Okay, so since output signal amplitude is much larger than input signal, input signal will be in millivolts, output signal will be in volts, and that is the reason why this is called as a large signal voltage gain. Okay. Now, under the conditions, this large signal voltage gain is measured and specified by the manufacturer under some certain conditions. And for LM741, under these conditions, large signal voltage gain happens to be, so A happens to be 200,000 typically. Look at the gain. And the conditions that are given are RL is greater than or equal to 2 kilo ohms and VO is plus minus 10 volts. That is 20 volts peak to peak. It simply means that if you are a manufacturer and if you want to measure the open loop voltage gain of this amplifier that you have designed, you must have a load, and this load is greater than, if it is greater than 2 kilo ohms, okay, then my A, if your input voltage is, if your output voltage is plus minus 10 volts, it is this voltage, then the gain happens to be this very large value. This is called as a large signal voltage gain. Got it, guys? Hello.
Yes, sir. Yes, sir.
Now, please remember this large signal voltage gain necessarily is an open loop gain. Don't forget this. Next parameter is the output voltage swing. Now for LM741, see this output voltage swing, which is denoted as VO max, is guaranteed to be between minus 13 volts and plus 13 volts under the condition RL is greater than or equal to 2 kiloohms. So it simply means that you can have 26 volts peak to peak undistorted sine wave for AC input signals. This output voltage swing therefore indicates the values of positive and negative saturation voltages. So what does this mean? It simply says that the manufacturer says, okay, my operational amplifier, what is the maximum output voltage swing possible? Okay, is without distortion, you can have maximum output voltage of plus 13 and minus 13. This is the maximum thing that you can draw from this. Of course, if the gain is more, if your input is also more, in that case, it will simply be saturated like this. This will be a distorted output. Okay, guys. Guys, are you there with me? Hello.
Yes, sir.
Yes, sir.
Next parameter is the output resistance. RO, just like RI, we have RO, which is the equivalent resistance that can be measured between the output terminal of the op-amp and the ground. For IC LM741C, this RO is 75 ohms typically. Right. Another parameter is the output short circuit current. I know these parameters are large in number, but you must understand this if you want to ever use operational amplifier, you should know all these things. For LM741, this ISC is 25 milliamperes. What does this mean? This means that the built-in short circuit protection, remember that there will be a built-in short circuit protection up to some extent. This built-in short circuit protection will withstand 25 milliamperes of current and thus protect the operational amplifier. But if you try to draw more current out of it, then this short circuit protection will be inadequate and the operational amplifier will simply get destroyed. Okay, guys, have you understood this output short circuit protection?
Yes, sir.
Yes, sir.
Then the supply current. Supply current is normally denoted as IS. It is a current drawn by the operational amplifier from the power supply. IS typically for 741 is 2.8 milliamperes. Okay. Another important parameter is the power consumption. Okay. This is termed as PC. Is the amount of quiescent power, that is when P in equal to 0, that is there is no input voltage. What is the current that is consumed? What is the power that is consumed by the operational amplifier? Okay, is called as the power consumption PC. Typically for 741, this value of PC happens to be 85 milliwatts. Why these things are important? Guys, do you know why these things are given? Why these things are important? Any idea about that? Please remember that whenever you design any circuit, okay, any application, power supply is one of the most important and critical components. And we must have a very strong power supply. Strong in the sense the power handling capacity or the current sourcing capacity of that power supply should be sufficient to operate your design. This is most of the times called as power budget. Estimating the power supply requirements is called as power budget. This is very, very important. If you land up with a very poor power supply, in that case, in the long run, your device or your circuit is going to won't be able to perform in the optimal way, the way it is designed to. Okay? So these two things are very important. Then you have what is called as the transient response. Now, any response to any network, we all of us know, response of any network to an input stimuli is composed of two parts. One is called as the transient response, and the other part is called as the steady state response. Okay, you must have already learned this. If not, see this particular thing. So whenever I apply an input stimuli, for example, I'm applying a step input here to a circuit. Okay, this is a step input. I hope all of you know what is a step input. Okay, this is time. So if I apply a step input to a system, normally the system has got a response like this. Any system, as a matter of fact, will have a response like this. So it will start here. And then, okay. So this is actually, up to this part I can say it is a transient response. And this is actually the steady state response. In that, we are normally what we do, if I try to find out what is called as a rise time. Okay, so this is the 10% value, the time that is taken to rise from 10% to 90%. Okay, of the value, we call it as a rise time. So this is called as a rise time TR. Let me do away with this. so that it will not get confused with the transient response. Okay, so 90% to 10% to 90%, whatever time it takes to arrive at that, achieve that particular value is called as the rise time. This part is called as the overshoot. Okay. So what is the transient response of a typical operational amplifier is given by the manufacturer. Okay. For LM, just a moment. I think this one note, yes, it was not responding. Okay, for LM741C, for Vin as 20 millivolt DC, that is a step signal. The rise time is given as 0.3 microseconds, and the overshoot is expressed in percentage, 5%. Okay, so these are the two responses, the transient response and the steady state. I mean the transient response specifically. Okay, guys, have you understood whatever we have done so far? Hello, guys. Hello.
Sir, please repeat this part, this graph part.
Last one. Just remind me tomorrow.
Yes, sir.
We already are out of time, so I don't want to clash into some other lecture. So please remind me this
Okay,
thing
sir.
tomorrow. Okay. So for today, I'll just sign off
Okay,
for
sir.
today. Okay, that's all. Okay.